Next, here I am going to prove an important theorem. uh, that is eigenvalues of hermitian operators are real. So proof of this theorem. So we know the for example, an operator is applying on a wave function. It gives another wave function. This type of equations we call the transformation equations, or in case if you apply the operator a and this wave function, it gives the same wave function and multiplied by the some constant value. This type of equations we're going to call in quantum mechanics eigenvalue equation. So these operators we already discussed in previous class. So in this equation here, A is the operator, An the eigen value. Here Cn is a eigen function. So here we are going to prove this eigenvalue of hermitian operators are real. So I'm going to use same eigenvalue equation. So here I'm taking A is the operator. It is applying on the wave function, nth wave function of the system, and it gives the same wave function and multiplied by some constant value. So now I'm going to multiply this equation by draw wave function from left side of the, okay, then this equation become like this. I sorry, draw function, this is operator, this is get function, equal to an, this is scalar, right? Scalar we can write outside of this operator, inner product of the two vectors. Okay, don't worry about this one. So this So here I'm going to give number of this equation. This is equation number 1. And similarly, here I'm doing the same operation what we did in the get function. Here I'm using the bar function. This is raw vector. Here I am applying an operator. This one is a dagger, right? Here I applied a operator a. Here I am applying a dagger on this get function. This a dagger applying on the get function, it gives the complex conjugate of the scalar number, eigenvalue number. So this is M state, right? Which is why I'm giving here the M state, psi M state. Now multiply by get vector is psi n of x from the right side of this equation. So in case if you apply here, be careful. This is operator. We need to careful here when we applying any uh, function get vector in quantum mechanics. This is scalar. Okay, this is operator. If you applying this operator here, it will apply like this: psi m a dagger. This one is into multiplication get vector psi n, not m. This one psi n equal to this is scalar, right? We can write outside this operation. So here I'm going to apply get vector on this notation, inner product psi m. The right side of this equation is psi n, and this is equation number 2. Okay, now I'm going to do one operation here. I'm going to subtract equation number 1 and equation number 2. Okay, see here, equation number 1 and equation number 2. Equation number 1 minus 2. So this gives, we know this function, this one is a, right? So observe carefully here. This is a operator, this is a dagger. From the definition of hermitian, we know the a dagger is equal to a, right? Then we can replace the dagger into the a. Then these two terms are cancelled. The remaining terms, these two terms, right? Then I'm going to write these terms like this. A, this is an minus am star into remaining this inner product psi m to psi n. So we know already the inner product of the two vectors. In case if m equal to n, this inner product goes to the 1, right? Or if it is not equal to, in case if m not equal to n, then it's go to the 0. So here I'm using this condition. Okay. If m equal to n, this notation is becomes to 1. Then remaining an minus am star equal to 0. Then an equal to am star. So here we already discussed the first initial here. If you apply any operator on a function, it gives the same wave function and multiply by some constant value. This type of transformation equations we can call here. It means in quantum mechanics we can call this type of equations eigenvalue equation. Here the constant is there, right? A suffix n, small a n. In case if you're going to confuse this a and the operator, then you can use this constant alpha here. Okay. So this small a is the number. That number means a real number, scalar number, eigenvalue of this equation. So here the complex conjugate of this eigenvalue both are equal. Then we can say this eigenvalues of hermitian operators are real. So eigenvalues of operators are real.